Welcome back. So we finished our introduction to geometric optics, and we've seen how mirrors and lenses work. Next we want to look at how these devices are applied both in nature and by man. So we're going to look at the use of optics in the human eye, in cameras, in microscopes, and in telescopes. I've put up the simulation again of the mirrors and lenses, so take a look if you haven't already. It's a nice way of visualizing how optics works. So we have a picture of a human eye here, and the cornea is the outer layer of the eye, and the light travels through the cornea and then through the aqueous humor, which is the outer layer of fluid in the eye, through the lens, which is a convex lens, and then through the vitreous humor, the inner fluid of the eye, and then finally an image is formed on the retina, which is at the back of the eye, and it contains cells that convert the light into neural signals. The key point here is that the convex lens of the eye produces an inverted and real image that forms at the retina. It needs to be a real image because the light needs to actually converge at that spot on the retina, so the retina can convert the light into a resolvable image. It is inverted, but that doesn't really matter since your brain can convert the image. There's a famous early study in psychology where a scientist wore glasses that vertically inverted his vision, and he claimed that after a few days his brain flipped the image and made it right side up. This is a great story, but it seems attempts to replicate it haven't really worked. You can get used to having your vision inverted and adjust to it, but people studied claim that the vision was still upside down. They just adapted to it. Remember, convex lenses are converging lenses. This does become a bit complicated because the cornea is a convex lens and the lens both act as converging lenses. The cornea is convex, and so you're going from a low index of refraction of 1 for air to about 1.38 for the cornea, and so the result is that acts as a pretty strong converging lens. So that's actually the larger part of the converging part of the eye. However, the lens is also part of the converging part of the eye, and the critical thing about the lens is that there are these ciliary muscles connected to it, and this changes the shape of the lens so that the eye can adjust its focal point. So the key idea here is that the eye forms a real image on the retina. To put this in perspective, let's look at a camera for a minute. So in a camera, we have an object that we want to take a picture of, a converging lens, and a image sensor where we want to take the picture. Or I guess it could be film if you have an old school camera. So in order to make sure that the picture is in focus, we need that the image to form exactly at the spot where the image sensor or the film is. So that means the distance from the lens is equal to the distance to the image. The distance to the object is the distance from the lens to the object, and then that means that it has to have the precise focal length in order for that all to work out. So in a camera, what you do is you change the distance from the lens to the image, right? You move the lens forward and backwards. That changes your value for the DI, and so because the lens is fixed, the focal length is fixed, so you adjust it until that basically it all works out so that the image focuses on the film or the image sensor. So by moving the lens forward or backwards, we can focus the image on the sensor. And the distance to the object is the distance from the whatever we're taking a picture of to the lens. The distance to the image is the distance from the lens to the sensor, and the focal length is whatever the focal length of your camera is. So in the case of the eye, we can't move the lens in the cornea of the eye forward or backwards. Instead, we change the focal length of the lens, so the ciliary muscles of the eye strain to change the shape of the lens. With the rounder the lens, the smaller the focal length. So let's look at how this works in our lens equation. So in our first case, an object is far away, so we are looking at a distant skyline of Richmond, say, and the light rays are all running parallel. So we need to have the image form at the back of the retina. That means that we know the distance to the object, which we'll just call infinity, and then we have the distance to the image. So the distance from the image is the distance from the lens of the eye to the retina, and we'll say that's about 2 centimeters. So that means the focal length of the eye trying to look out into the distance has to be equal to the distance from the lens to the retina, 2 centimeters. So that means the focal length is also about 2 centimeters. There's also a far point. So the far point is the farthest distance that an eye can focus. So if an eye cannot have a focal length of 2 centimeters, let's say it can only go to 1.9 centimeters, then there will be a distance beyond which the eye can't focus. In a normal eye, it is infinity, but if you are nearsighted, then that far point will have some sort of distance. Next, let's look at the near point. So how close can you move an object where you can still focus on it? Try it. If you bring something right up to your eye, it will be blurry. You'll need to move it away before you can focus on it. We will call it about 25 centimeters, and that means the distance to the object is 25 centimeters, and the distance to the image is still 2 centimeters, because it is the distance between the lens and the retina, and you can't change that. So when we solve for the focal length, our focal length now is 1.85 centimeters. Notice that as the object moves closer, we need our eyes to have a smaller focal length, and we do it by sort of straining our ciliary muscles to make the lens more convex, so the focal length becomes smaller. Okay, so that gives you an idea on how the human eye sort of works. Basically, the image has to form on the retina, and so then your muscles in your eye adjust the focal length so that wherever that object is, that your image forms exactly on the retina, so it is visible and easy to see. If that image forms elsewhere, then it's going to look blurry in your eye. Okay, so you have a few problems to do, and next we're going to start to look at corrective lenses. Good luck.